to know about their platforms, their applications, and so we will now start with Professor Marcassa. Luis Marcassa.
Thank you, Muniz. Muniz was my undergraduate student when I was a PhD student, so I have been doing Rydberg atoms for a while already, so it's like, by now, it's like 25 years, something like that. So Rydberg atoms are not new. In fact, if you go back and you look for Rydberg was like this Swedish that discovered that when he looked at the Baum series, he was able to come up with an equation, that could explain the hydrogen atom lines. In fact, he was able to explain all the lines of any atom using a similar equation, okay? So that's the success why he got his name on that. And he's from Lund University. In Lund University, they used to have a bar at the university called Rydberg Bar, and I am one of the associates to that bar, That was before the pandemic, of course. And then what happened? Of course, this is the end of the 19th century, and then came Bohr. Bohr explained why Rydberg was right on his equation. And basically, if someone asks me what is a Rydberg atom, I like my Brazilian analogy of football, So a ground state atom is the size of a soccer ball, and a Rydberg state atom is the size of the Maracanã Stadium, So that's the scale that we are talking about. In fact, the ones that we are talking about the things that are like the size of a human blood cell. So that's such the size of the atom. We are talking about quantum numbers on the order of 60 up to 80, 90. It depends on your laser, And because the electron is very far away from the nuclei, it feels very much any small field that comes around. So any small magnetic field, electric field, electromagnetic field will perturb the Rydberg atom, and it's easy to see, okay? Well, of course, to have a Rydberg atom, you need to excite it, and in order to do that well-controlled, you have to do it with lasers. And of course, it took a while to get lasers settled enough, in good conditions that we could really produce those atoms, okay? So what is the best way to detect it? It's called electromagnetic-induced transparency. So we are going to do an EIT. And usually, in our case, we have rubidium. So we have the 780 laser here. And then here, we have a laser that's 480 nanometers, okay? So that's the scale. Why rubidium? Because I have the lasers for that, If you want to do cesium, you could do cesium as well, because this first photon would be 850, and the second photon would be around the green light, more or less. So those are the two best candidates for doing Rydberg atoms, just because diode lasers are available in this region. So what you do, you have a sample of ground state atoms, you shine the 780 light, and you monitor the transmission, okay? So as you scan the probe laser, which is this first laser here, you scan the probe laser, you will see the absorption profile, a typical absorption profile from any atomic line, okay? Well, if you come and you couple this 5p state to a Rydberg state, which in this case can be either S or D state, because you need to have a dipole transition, a dipole allowed transition, what happens is if you play this game properly with a lot of power in this second photon, it happens an interference. So you can imagine, in simple terms, that in order to electron go from the 5s to 5p, it has two paths. It either can go straight, or it can go and go around the Rydberg level and come back. Okay, and this generates an interference which is destructive and opens a window of transmission. So suddenly, the light that was being all absorbed by the medium, now it is transmitted. So by looking, and this usually is is smaller than the line width of the atom. Okay, so by looking at this. Now, if I come here and I add an extra microwave frequency that's going to couple this Rydberg state to some other Rydberg state, what's going to happen is that this state here is going to split. You know, you can think that as the outer tone effect, or you can think as like having a dressed atom picture. You know, it's just perturbation theory. So when you add one more field here, it splits the level. And by looking at this splitting of the level, I can tell you exactly what is the microwave that's going on. Okay, so how do we do it nowadays if you are working with microwave? So what do the engineers do? Oh, we have an engineer in the audience. Okay, at least one. So what they do is they have a horn, you know, that usually, if you go back to your electrical magnet course, because of the dimensions, it only works in a range, you know, and you take this signal, you put in some electric circuit here, and you can come and you can tell, oh, look, I'm looking at this frequency right now, okay? Well, this has some problems, because like if I wanted to really calibrate the field that is in this antenna, is complicated, you know. It's a very hard procedure to calibrate antennas to know exactly what is the field that is getting to that. Second, when you make an antenna, next antenna is not going to be the same, you know. So there is always small differences in the antenna. And even if you wait, as its age, it is oxidized, so it changes also. So it is bad. Well, here comes our Rydberg atom. So what we have the 780, we have this blue light, and we look at the transmission. First thing, it doesn't matter what is the frequency that I excited here. You know, I can excite any frequency I can put here, and it's going to work, you know. If I go to a very high quantum number, the level separation is going to be on the order of megahertz, and I can use to detect the microwave in the megahertz frequency. If I go very deep in the potential, in the Coulomb potential, it's going to be terahertz. So just by choosing which state I'm selecting, I can make this sensor work between megahertz to terahertz, okay? So this is a very powerful sensor. Another thing, this is an atom. So the electric dipole moment in the absence of any field is well known. You can calculate that. So you can come up, and this is going to be directly traceable to the international standard. So if I look on this transmission here, and I see this splitting, I can tell you what is the field that is exciting those atoms. I have to hurry up because Sergio is looking at me already. So this is how the engineers like to call the microwave region. If I'm wrong, you can correct me, Daniel. So it goes from VHS, you know, I think this is when you are about my age, that was the TV operating this region, then it came UHF and so on. But here, see, there is radar, microwaves, telecom, and all these other kinds of here. And those strips on black lines are where this has been done already, okay? So this has been done, all this region has been covered from megahertz to several hundred terahertz to detect those fields. So it is easy peasy. You just have a glass cell full of rubidium atoms. You know, you shine the lasers, you look at the transmission, and you can detect the microwave. So just to give you an example, this is just look here, this blue line is when you have no microwave. Forget about the other stuff. It's just look at the blue line. The blue line is the transmission through the sample, and you have there is more transmission when you are in resonance with this state. And when you add the microwave, this guy is going to split and separate in two peaks, and by measuring this separation, you can tell exactly what is the field, okay? This is very interesting because DARPA is this last year, put a lot of money on this to generate systems that can detect the microwave using Rydberg atoms. There is a company that one, a former student of mine is part of. This is called Rydberg Technologies. There is another company in Ontario, which is a friend of mine, is the guy behind that. And recently, we were lucky enough to convince Embraer that we should start on looking at that. Because if you don't know, but in September 24, the US government passed some legislation prohibiting the selling of quantum technology, okay? This guy, this former student of mine, has been developing this stuff for the US Army. My friend is developing this stuff for Airbus. Okay, so there is a lot of stuff to be done. This work is supported, of course, I should say, otherwise we'll be kicked out, is supported by FAPESP, by the US Army government, and a tiny bit, very tiny bit by CNPq. Okay, I like to mention that that's a very tiny bit. Okay, thank you for your attention.
Thank you, Marcassa. So now we have João Paulo Snecker from the CBPF talking about superconducting devices. So we will alternate between atoms and solid-state-like systems.
Tá no seu bolso, Marcassa? Você pega pra gente? Obrigado.
Alô, alô? Alô, alô? Alô, alô? Então, dá para ouvir aí? Ainda não. Okay. Okay. So, good afternoon, everybody. João Paulo from the CBPF, and I will be talking about superconducting devices, but more in a way of what facilities we have now developing. I'm mainly a guy from nanofabrication and not from quantum information and so on. So my history goes back to nanomaterials, nanomagnetic materials, and nanofabrication. But I'm involved now in this project, and I would like to show you a little bit. Just for the ones who doesn't know, the CBPF is one of the units of the Ministry of Science and Technology, belongs to this very much big units spread all over. We are 17 units. Some of them are very well known, like the Observatório Nacional that has almost 200 years. CBPF has 75 years. And we are promoting this kind of thing, research, innovation, education, and outreach for the community. We have a very broad actuation in physics, but I highlighted some of them in which these projects are direct related, although we have many other things going on in CBPF. All the development we did starts because of Lab Nano. Lab Nano is a facility which was installed in CBPF in 2010. And it was one of the first, along with LN Nano in the CNPen and all the microscopy park in CNPen, that started a multi-user nanoscience and nanotechnology laboratory in which we had nanocharacterization with electron microscopes and nanofabrication with electron beam lithography and other lithography stuff. More recently, we started to build, in this quantum technology project, some superconducting devices as a platform for quantum computing based on qubits, based on Josephson junctions. So the idea here is to be able to construct this is a waveguide basically, but it's made of niobium, so at low temperatures is superconducting. And as I will show you, we go to very low temperature in this case. And we can inject signals here in this waveguide. It is synchronized to certain frequencies. And all those positions, we are able to build aluminum and aluminum oxide junctions that are Josephson junctions. They are the base of the qubit unit. The qubit, as you know, is the transistor of the quantum computing. So the role of the transistor in classical computing is performed by the qubits in the quantum computing. And so we do the design of the systems, and we were able to do this, to fabricate them in sputtering machines like this. In fact, this is a Disneyland for constructing. It has an sputtering chamber, an ion milling chamber, and an electron beam evaporation chamber. So we can build many special materials inside. And we also just acquired a dilution refrigerator to drop down the temperature to milli-K. So here we can go below 7 millikelvin. And this is necessary because of the noises that are involved. The signals are very tiny. So we need the system to be very cold in order to be able to measure it. Yeah? Besides this project, we also have in the same mainframe a project of quantum communication, a quantum network, using either the fiber optics already installed in the city. Those are part of the fiber optics that communicates all the institutions in Rio and in Brazil. In fact, we are one of the nodes of the RNP system for transmitting and academic and other things. Yeah? And we have now a link, an optical link from CBPF to the Universidade Federal Fluminense, which is made by lasers. And we can send, this is at the UF, and this is at the CBPF, we can send and receive a laser to promote quantum protocols for communication for quantum encryption. So what are the possibilities and what we can do in this quantum lab? The idea of this quantum lab is to be, of the whole facility, is to be an open lab, much more like the CNPEN is. So it's to receive projects, to receive researchers with an infrastructure that can be used by the whole community. So we will be able to do fabrication and characterization of superconducting quantum chips based on niobium, aluminum, and aluminum oxide, and similar materials. By now, perhaps in the future, we will be able to do more. We are able to by means of laser lithography, to build this kind of chips, that kind of waveguide I showed you first. And by electron beam lithography, we're able to do the Josephson junctions to be the quantum bit, the qubit basis. And this chip will be then characterized in the dilution refrigerator from Blue Force. And so these are more examples. This is one of the waveguides produced by laser lithography. Here are a bunch of them. And this is an electron microscopy of the Josephson junctions amplified that was fabricated here. This junction was fabricated in collaboration with Unicamp, with the group, one of the groups, Francisco Rochinal in Unicamp. Because up to now, we didn't have this equipment to produce the sputtering and so on. So we did the lithography in Campinas, in Rio. We did the niobium in Campinas, came back to Rio, did the lithography, came back to Campinas, did more depositions, and finally we arrived to this final product. Yeah? This is more or less what happens inside. So we inject the signal here in this waveguide. The qubit is here, and so by means of a special electronic and some attenuators and so on, we can inject signals, radio frequency signals, to the system, to the cavity, And depending on the state of the qubits, the resonant frequency of the cavity changes. And by means of this, we can detect in which state the qubit is, and as well, we can, if they are coupled, if they are entangled, we can make some protocols of quantum computing and so on. And this is the base of what Google and other Amazon and so on, other computers are using and are providing for use for the community. You can access the Google and the IBM computers to use this kind of technology. So the idea is to be able to build this kind of things and to be able to give access to the community to them. So this is one of the example. We can do modeling of this, of course, and this curve behind is one measurement we did, and this is the simulation, the modeling of the system. We can also do all the simulation and design of the waveguide by using Qiskit and using other softwares like ANSYS HFSS or using COMSOL. So we developed the technique to do simulation of this waveguide and so on. That helps very much the development of the systems. And we will be able to do the whole characterization, the injection of the signals and recovery of the signals with multiplexed electronic measurements. This will be installed soon as well. And this is just, again, the room of the quantum communications. And we also have a Microtime 200 confocal microscope from PicoQuant that you can do NV centers. So the whole project involves NV centers, quantum communications, and superconducting devices. So this is the quantum lab that we are doing. Yeah? And for the future, what we are planning is an expansion of CBPF in what is called Parque Tecnológico da UFRJ. This is in the campus of the university, the Universidade Federal do Rio de Janeiro. It's the far border of the campus. And in this Parque Tecnológico, there are many companies. This is the ocean tank from, it was from Petrobras, now it belongs to the Instituto Nacional de Pesquisas Oceânicas. This is the Ambev Research Center. This is another company. So there are many innovation companies installed there, and CBPF it's negotiating, and it's already finished to get a position on this part of the island. And the idea is to build a lab, a facility, a new facility, in which we will have not only a nano center for quantum technologies and other research, but also scientific instrumentations, artificial intelligence, and a physics and innovation hub. So the idea is a place where you can do innovation with this high-end technology to promote startups and so on, to go a little bit far away from the mainly academic side, but keeping an eye in advance of science. So this is more or less what I had to talk. I hope I was in time.
Perfectly.
Thank you.
Thank you. Okay, now so we go back to atoms. Deep Cote.
Qualquer lugar, só para não ficar.
Alô? Não, fica no desktop, né? Não, não. Eu já fiz o download. Talk.
Eu acho que está projetado essa tela já, se você vai querer para trás. É para voltar no começo? Acho que sim, sim.
Okay. Good afternoon, everybody. It's a pleasure to be here. Thank you to the organizers. I will present one experiment. We have two experiments. One experiment Raul Teixeira is in charge of, and the other experiments I'm coordinating. And on this experiment, we have two research lines in fundamental physics, and this is what I'm going to present to you today. So it's about quantum sensing with entangled atoms and matter wave inside cavities. Okay, so these are the two research projects. So one research line would be quantum sensing 2.0 with spin-squeezed atoms, with the long-term goal to achieve super radiant lasing, for example, sensing below the standard quantum limits. And the other would be matter wave interferometry 1.0, so with a special ingredient, which would be real-time monitoring of Bloch oscillations. Okay, this is our experimental setup. It's a scheme. So we have a laser pumping a ring cavity. The ring cavity is a so-called bad cavity because it's a good cavity, but it's bad because the kappa is very large in comparison to the natural line width. We take an atomic species which has a very strontium, which has a very low decay rate, so that gamma is much less than kappa. So we can completely neglect about spontaneous emission. The only decay process, the only dissipation process that plays a role in our dynamics is really cavity decay. Okay. So then we have a cavity mode, which is described by operator A, and we have a collective spin, which is just the sum of the individual atomic spins. All the spins interact with the field in the same way, so we can employ the so-called Dicke model. This is the Hamiltonian of the Dicke model. The first term of the Dicke model is just the pumping of the cavity by the laser. So it's a coherent contribution, but this is not the most interesting part is the atom-light interaction. So the collective spin can go up if you provide a photon, if one atom absorbs a photon, or it can go down if one atom is going back into the cavity mode. Okay, so this is an interaction between the harmonic oscillator of the light mode and the collective spin. Okay, as you see, this is a linear Hamiltonian. Like everything, quantum mechanics is a linear theory, so everything needs to be linear. However, we can do an approximation and eliminate one degree of freedom, which is a cavity, from the equations of motion. Okay, because we know if kappa is very, very strong, then whatever the atoms will do, the light field in the cavity will immediately follow. So it's not an independent parameter, and the only real parameter which we want to control is the collective atomic spin. So if we solve the Heisenberg equation for the steady state, for the cavity degree of freedom, we plug it into the Hamiltonian. What we get is an approximated Hamiltonian, which turns out to be nonlinear. So like always in physics, nonlinearity is always an approximation. Nature is intrinsically linear. If you want to have something nonlinear, you have to make an approximation. Okay, so we have an approximation. So we have a Hamiltonian which is now nonlinear, but it's much simpler. So the nonlinearity is a trade-off of this approximation. Okay, and this is interesting because this is a typical quadratic Hamiltonian that you use for doing spin squeezing. So if you have your atomic cloud and you tune your parameters, it's a combination of experimental parameters that you can arbitrarily tune, and if this collective spin is quadratic. Now, if the Hamiltonian is quadratic in the collective atomic spin, then you have an interaction which can drive your collective atomic spin into non-classical states, for example, spin-squeeze states. Okay, this is all you have to do. Okay, and so spin-squeeze states are quantum technology 2.0. Now it's an angled state. So with I think. Daniel already mentioned briefly that you can improve that you can improve nowadays metrological devices like clocks or matter wave interferometer, like interferometer, if you want to go beyond the standard quantum limit to approach the Heisenberg limit. This is what you have to do. And in the last talk, I've seen also that, I think it's Danielle's talk, there are nowadays experiments which are already reaching the standard quantum limits. No? I remember that Philippe Boyer a few years ago, he said there's plenty of room for standard improvement of optical clocks and interferometers. There's no need to go for spin squeeze states, but in recent years, there's a paper that I didn't know yet. The clocks are already at the limit, and now it's going to be interesting to go beyond this limit. No? Okay, so we have constructed this lab to monitor, to see this effect. I make a zoom on the main vacuum chamber, which is here. Okay, all the rest is lasers that you need to control the atoms and to probe the cavity. I go a little bit fast. Here's our cavity, where we pump light, which is circulating in the cavity. Then we make an atomic cloud. We cool it to very low temperature. We need about 1 microkelvin temperature. We have 200,000 atoms at 1 microkelvin temperature that we put into the cavity. Here you see atoms which are at this temperature, which are trapped by an optical tweezer, which is made by the mode of the cavity. So the atoms are really trapped here in a standing wave potential because we pump the cavity from both sides. And then you can probe the transmission of the cavity. And what you do is you look at the normal modes. And the normal modes, normally, so here we can scan the frequency of the laser with respect to the atomic transition. We can also scan the cavity with respect to the atomic transition. And what you normally would expect, if it was a classical scatterer, would be a normal mode splitting of this, an avoided crossing of this normal modes. Okay? So without this central feature. The fact that we see a central feature points to the fact that we have something nonlinear going on. Okay, and this nonlinearity is so this here is a proof that we have probably a collective state. It's not a direct proof because we haven't seen a spin squeezed enhancement of metrological signal yet, but we are very confident that we are in the good regime. So we can reproduce this by theory, of course. So the fact that we are here, that here you see something and not simply a blue area, is due to the fact that we are saturating the atoms very strongly on resonance. So we are exactly on resonance and saturating the atomic the atoms. And this is possible because we have a very low spontaneous emission rate. So we are not fooled by heating or something which comes along with spontaneous emission. Okay, and then. Yes, so recently there have been some interesting proposals here that show that this driven dissipative system. So you drive your system with a laser, and at the same time it dissipates by transmission through the cavity mode. That this system automatically evolves into a spin squeeze state. I try to visualize here. This is a Bloch sphere. This is a generalized Bloch sphere. So you know the Bloch spheres for one qubit. If you put all the qubits one on top of the other, you have a Bloch sphere which has the size of the numbers of atoms. Okay, and here you see that if you plot the Wigner function, for example, of the state, you see that it's squeezed in one direction. Okay, and this is a state which comes automatically out of this setup. You also see that that the projection of the spin squeeze states on the plane here is round, so it's a coherent state, and this coherent state is nothing else than the quantum correlations of this cavity field. So unfortunately, the fact that we have spin squeeze states here, we cannot probe this fact by looking at the coherent state of the cavity light because it's coherent, no? And you cannot say, okay, I see a coherent light, and so I necessarily have spin squeeze states here. This is too easy. No? It could also be another effect which destroys the spin squeezing and makes the light coherent. On the other hand, so that in fact there are two possible states which are connected by phase transition. It is also possible to show that if the atoms are brought into another state which is actually coherent, then the light which is obtained by projection on the Glauber plane here would be squeezed. No? So Yeah, so this is the system that we have right now, and which we are going to study now. So what we have done already, we observed the bistability in a bed cavity, which is a proof for the non-linearity. The fact that we have large atomic saturation achieved on resonance means that the dynamic is intrinsically quantum, because saturation is an intrinsic quantum effect. No? You cannot saturate classical systems. Okay, and then what we need to do, we have to understand better the quantum fluctuations, the phase transition between the two states. We have to find optical spin squeezing witnesses, which might be a complicated feature, and we would like to be able to generate a real inversion of the atoms in order to be able to have supervariant lasing at some point. Okay, the other experiment has to do with meta-wave Bloch oscillation. So we take ultra-cold atoms. It doesn't need to be a Bose-Einstein constant. It can be individual atoms. Normally, what you do in order to construct gravimeters, you take a condensate, you split it into a path. Those two passes they have different trajectories in the gravitational field, and when they are recombined, they have some interference fringes, and the interference fringes tell us the gravity which was active during this time when the atoms were separated. There's another way to do it, which is looking at Bloch oscillations of a meta wave inside a periodic potential. The periodic potential in our case is just a retroreflected laser beam. Yeah, so when the atoms are at zero temperature, they have infinite de Broglie wavelengths in this direction. When they are accelerated by gravity, they come into resonance with a standing light field, and they are backscattered, and so they do Bloch oscillations like jumping on a trampoline. And the frequency of these Bloch oscillations is strictly proportional to the gravitational acceleration. So by just monitoring this frequency of these oscillations, you can monitor gravity with very high precision. And so this has been done in other groups already. So our idea is to do this in a nonlinear, in a non-destructive fashion. So not only we want to have the meta wave doing Bloch oscillations here, but every time that the Bloch oscillations occur, that light is reflected from the meta wave, is shifted by the Doppler effect. So the Doppler effect tells you the velocity of the Bose-Einstein constant or the meta wave, the instantaneous velocity. But the light is not scattered in other directions due to simultaneous emission. It's recycled in the cavity, and eventually it's leaking out of the cavity, where it can be probed here continuously. And so continuously monitoring these oscillations, you can monitor gravity in a continuous fashion with a single meta wave. You don't need to prepare a new meta wave in order to get a new point for every time here on this axis. Okay. So that's it. This is what we have done. We already have 200,000 atoms cooled down to the single photon recoil limit. And we have been able to trap the atoms in a lattice which is so shallow that it only allows for a single vibrational state. There's only room for a single vibrational state, which is necessary to observe these Bloch oscillations. And the next steps are looking for signals of the Bloch oscillations and really try to see these Bloch oscillations. So these are the people who are involved in this experiment. Raul is here. Dalila is here, Gustavo here, and Claudio. Claudio is here, okay. So that's it. Okay, thank you.
Thank you, Felipe. So now we go back to solid state, again, with Professor Thiago Alegre from Unicamp.
Nunca sei se está certo isso aqui assim, não, né?
Eu acho que tem que abaixar um pouco mais o... põe atrás.
Sim. Não, não, eu vou fazer na mão mesmo, porque não vai dar para... deixa eu fazer o seguinte. Peraí. Então, é isso que eu vou fazer, porque acho que vai ser mais fácil. Peraí. Aqui, ó. Ver se está funcionando. Ok. Yeah. Okay. Good afternoon, everyone. So, thank you, Sergio, for letting me here. And I will go back to solid states. And I'll try to convince you that actually we can use optomechanical devices also in this quantum world. And that's the main idea here. And I'll be kicked off by someone else in 8 minutes. That's the idea. 2 minutes and I'll be dead. So the idea in optomechanical device that you have a light matter or light sound interaction. And this has been done for a long time already, either on waveguides or on cavities. So on waveguides, one of the most simple one is like the brilliant scattering that you see on an optical waveguide, on an optical cavity, or on an optical fiber. If you shine too much a laser and crank up the power, you start seeing vibrations from the silica, and then you see the backscattering light from the silica. And on optical cavities, you take advantage of this resonance mode of the optical device, and therefore you enhance this coupling there. And the main idea here is simple. For this toy model, I love this toy model. Everybody that has seen me knows that I love it. So you have an optical cavity, a very simple one, like a Fabry-Perot, with length L. And if you let one of the mirrors move back and forth, you can actually know how much is the frequency shift due to this motion. And this is actually what is called the frequency pooling. And as you see, this depends inversely with the length of the cavity. So the tiniest the cavity, the largest the frequency pooling. So the tiniest the cavity, the largest will be the frequency shift, optical frequency shift when you change the size of the system here. And how does this translate to the quantum world? So the main idea here is this toy model here have an optical system, which is this one here, and a mechanical system, which is the spring attached to a mass. Both has their internal energy, and you have the coupling in between them due to this frequency pooling. Okay, so this frequency pooling and actually scales with the number of photons inside the cavity. That's very important because you can control the amount of coupling with the position or motion. Okay, and you can actually just rewrite this in a more easy way to understand. To take a look at the connection to the B operator here, and using a normalized constant here for the frequency pooling. The important part here is that since you have the cavity, the optical cavity, it also serves as a filter. And then you can select which is the interaction that you are doing there. So although you have an interaction that scales with the number of photons, depending if you are putting your laser to the left side of your cavity, which then promotes more scattering in resonance to your cavity, only the sideband that has higher frequency is actually on resonance. That ends up to be a beam splitter Hamiltonian. And if you just move, and that actually, what that means in terms of a real world, I'm not sure if it's showing here, yeah, is that you can actually cool down the motion because every single photon takes away one phonon from the system to scatter light to a higher frequency, okay? Just by changing the frequency to the other side, you can actually come up with a squeeze type Hamiltonian, because now every single photon in the system creates a phonon, because now only the lower frequency or lower frequency photon is resonance to the cavity. And that gives rise to this amplification of motion of your system, okay? So, and this is just like by changing the phase of your interaction. That's the idea. It's like a little kid on a park. If you push in phase with the motion, you increase the amplitude. But if you go and push out of phase, you actually dampen it down, okay? And this has been done in lots of devices and actually lot of sizes actually. So since like I think the most famous one is actually the LIGO, which is the gravitational wave interferometer, which has like kilograms mirrors to cold atoms, as we saw here, that also can push that. And we also have our own zoo at Unicamp that we have explored basically microfabricated device on gallium arsenide, on silicon, or on waveguides to push that. And I'll try to be fast. Let me see how many minutes we have here. Oh, I'm like plenty of time. And I just want to try to convince you that actually you can have this optomechanical device to be a quantum interconnect. So first you can actually connect like photons to photons by the phonon. So what you do here is actually you drive a phonon, and this phonon talks to another cavity, another frequency, which then talks to a photon. So you can actually transfer information from a photon to a photon via a phonon. You can also connect to solid-state qubit, like NV centers that we had this morning, and actually drive from the photon. You drive a phonon that changes the lattice constant of the NV center or this solid-state qubit, which changes that levels that we heard this morning from Carmen, and that changes the frequency. And you can also have the last one, which is you drive photons to phonons, which then these phonons can actually, through a piezoelectric device, couple to the microwave devices there. So then you are translating from photons to photons, but photons on terahertz to photons on gigahertz. Okay, and we have been working in some of this device here. This works in collaboration with Professor Simon Globacher. And just to point again about the device itself, so you see like 5 micrometers here. This is the size of, roughly of the size of this cavity here. And if I think on Marcassa's talk about the atom, our atom here, which is the phonon, or the phonon mode, is also on the order of micrometer size. Okay? And the main idea here for the teleport experiment, I'll try to go, it should be hidden, but it is not. Let me go back here. I think, I'm sorry, because it should be hidden here. I think it's easier if I go here, this one here. Is that you have like 2 separate cavities, and you can shine a laser which goes either to cavity A or either cavity B, and you create a phonon state, and they are entangled. And then you can have like your Alice and your Bob, which then share an entangled state. And what you do is you mix Alice state with an unknown state, and tell Bob through a classical channel what kind of measure he has to do to recover the state. And we show that that's possible to do with this device, where like the phonon states are your quantum states that you are actually encoding and reading always through the optical channel. I think that's the important part. One key ingredient here is that this kind of experiment is extremely slow. So it takes like about like 25 to 30 days to take this data here, because we have residual heating. So we need to have a better way to block actually the environment from your system here. And we have been doing that on 2 ways. One of them is these 2D systems, where like it's very simple idea. It's just like you say like, okay, I don't have a 1D state where heats can only flow from one side, but now I have a 2D device that actually can have heat sink from a 2D state. That had been shown. That's not our work. That has been shown before, that you can improve. But the design that we work with the guys from Stanford we are a factor of 10 better than this result. So we are trying to get as isolated as possible from the environment to process our data. And the other thing that we try to do, we also did in the past, was to explore a dissipative coupling. So again, we heard about dissipative cavities now. So we know that the cavity is not perfect, so it has losses. So how to come up or to use that? And I also want to highlight again the size of the things here. So we do also have like on the order of like couple microns here on the size of your optical cavity and your mechanical cavity. And I promise that I'll be on time. I just want to explain what is the dissipative meaning of this. I explained that if you change the size of your cavity, you change the central frequency, but also if you change the size of your cavity, you can also change the losses of your system here. So the pictorial way to see this is actually that if you have a little bit coming back and forth, it scatters light. So then it changes the losses. And that has the same coupling when you write down the Hamiltonian as the dispersive. But now you are using something that is inherent of the system, which is dissipation, to actually to understand or to couple to the mechanical motion then, okay? So again, brief ideas, but everything's not everything's nice. So these 2D systems show that we can be in the quantum world, we can do teleport, but there's still residual heating. We come up with a very nice idea to take it out the heating here, but then you still need to couple to the superconducting device. And on the dissipative, we still need to do low temperature experiments to see if that actually helps in the same way, okay? And I'll just leave you here with the collaborators and our funding agencies and our group that this year didn't look like the churrasco. People were just complaining a lot of it, but maybe we'll have soon enough. Okay, thank you so much.
Thank you, Thiago. So now, last but not least, certainly, we have Hans Flores from Federal University of ABC.
Deixa isso aparecer.
Vou te acompanhar.
Ah, tá. Precisa para compartilhar aqui. Hans. Deixa eu só pegar aqui. Já tem um aqui, na verdade, conectado. Dá para compartilhar aqui. Deixa eu só... Yeah. Okay, thank you very much, Sergio, to letting me present to come here and tell you a little bit about the project that I'm going to develop at the university, the Federal University of ABC. Sorry, the image is a bit cut, but well, anyway. So the idea is to develop an atomic magnetometer improved with the squeeze light. So basically, anyway, the idea of the great thing that make the atomic magnetometers to gain some attention was the study of the brain function. And so for medical diagnosis, there were some kind of sensors, like squid sensors, like in this machine, that can be used to detect signals emitted by neurons, right? And the problem with the squids is that, as some of you, of course, already explained, they work at very low temperatures. So it makes that this kind of test that you can do here, it has a very high cost of operation. So then recently in this work led by Professor Matt Brooks at the University of Nottingham, they showed that it is possible to use these kind of sensors, which now there are startups in US that you can find these atomic magnetometers that you can put in a customized helmet and do this kind of test. And with this kind of sensors, we can reach femtotesla sensitivity. And it's been shown that actually it can go down to sub femtotesla sensitivity. So with this kind of sensors, you can do this kind of test, and there is no cost of operation compared to what you can find with the squid sensors. And also you have a very high sample rate for detection and the high sensitivity. So this was one of the main applications that really attract the attention of researchers. Then more recently, the idea is looking for different applications. So it's been shown that it is possible to use atomic magnetometers to do magnetic imaging of objects, now in the scale of more than 1 centimeter, right? But when it comes to nanometers, then it really needs to be done with MV centers. But when it's for higher dimensions, then it can be used this kind of magnetometers. Also, it's been shown that you can do imaging of objects hide enclosures, like in this one. This has applications in airports, looking for hidden objects and things like that, right? And more recently, it's also been shown that it is possible to use these magnetometers to do battery diagnosis. So in lithium batteries, the idea is to look for defects of the battery. But if you do it with X-rays, you end up damaging the battery. So the idea is how to do a non-destructive measurement of these defects, and that's why it's been used atomic magnetometers to do this kind of measurements. And also, it's been in this work, it's been shown that it is possible to do magnetic communication, because in situations, underwater situations, or in mining, for instance, where you don't have the standard communication with GPS or things like that, it is also possible to do magnetic communication using these kind of sensors. And more recently, now it's been shown that you can couple these magnetometers, atomic magnetometers, with noble gases. And by doing this coupling with the magnetometers, you can have an enhancement on the sensitivity of the magnetometer. And this enhancement is used to look for action-like particles for dark matter. So these are more or less the most recent applications of this kind of sensors. And basically, how they work is that you use light to prepare the state of the spins, right? And as there is a presence of the magnetic field, then the spins start precessing around the magnetic field. Then this precession is probed by an additional beam here, which is the probe field, and that's how we read the presence of the magnetic field. Of course, there are many terms that contribute to the dynamics. One of the main effects on the dynamics is the decoherence. Depending on where you are, the decoherence can destroy this precession. But different from what Carmen was saying, that MV centers, they are actually not using any kind of superposition or anything like that. When the magnetometers, they operate at the serve regime, which is the self-relaxation-free operation of the magnetometer, what happens is that the collisions between the atoms, they are so fast that at the end, they end up synchronizing all of them when we have very weak magnetic fields. So in fact, there were works in which they showed that when the atomic magnetometers operate in the SAIFR regime, the spins of all these atoms are actually entangled. So these kind of sensors, they actually operate with entanglement when they operate in these kind of situations. This is not the only possibility to do atomic magnetometers. But in general, for instance, those that I show, the commercial ones, they are scalar magnetometers. So they just measure the strength of the magnetic field, but you don't have any information of the direction of the magnetic field. So, but there are some applications for even for medical applications in which is interesting to know not just the longitudinal magnetic field, but also the transverse field. So in that sense, it is important to have a vector magnetometer in which you can extract or have information of the direction of the magnetic field. And this is something that we demonstrate with Professor Thomas Verhulst with this work, in which we actually prepare a different kind of spin state. But it's a spin state that allows us to, if there is a change of the direction of the magnetic field, like in this case, not just in this direction, but if it is tilted, something like in this direction or even up, then we can have information of which direction is pointing out things. So this is what we show, but there are some drawbacks and there are some points that we need to improve. So there was at room temperature with some kind of vapor cells. But in order to increase the sensitivity, to actually reach sensitivity down to femtotesla, we need to use two strategies, either work on the magnetic sensor, and in this sense, it means that we want to reduce the size of the sensor. Instead of using large vapor cells like this, really work with vapor cells of 5 millimeters or 3 millimeters like in this one. And also the idea is to work with microfabricated vapor cells. But the other strategy is to use a different kind of light source to probe the magnetometer. So because I don't have that much time, I probably just jump on. So I will show you very briefly what are the microfabricated vapor cells, which are this one. This is like a typical size of a vapor cell, but we can start working with microfabricated cells. And the idea is to really have small sensors for this kind of applications and really get into this kind of regime like what is being done in NIST or what is being done by QSpin, which is already the startup in US. And very briefly about the squeezing light, we can also use the atoms to produce a squeeze light, and that's something we show with in collaboration with Professor Marcelo Martinelli at USP and Professor Alberto Marino in Oklahoma. And basically what we did is we showed that it is possible to put the atoms inside a cavity, more or less what Felipe does, but he's doing it with cold atoms, and we are doing it at room temperature, or well, actually hot vapors. And we showed that it is possible to produce entangled beams, like in this case. And so we produce these twin beams at relatively low powers, different from the case of not having these mirrors. When we don't have these mirrors, then we have to operate at 400 milliwatts of power. So in that sense, the OPO is more efficient than an OPA. And of course, we showed that we have a squeeze light, this compression of the intrinsic noise below the classical limit. So this squeezing is the one we can use to probe the magnetometer. As in this case, sorry, let me see if I can go back here. Well, as this image in which by using a squeeze light, you can now detect very weak signals from any sensor that is based on optical reading. So just to sum up, so the idea is to have this kind of light source, But one advantage is also that we can different from OPOs with crystals, which then if you want to change the wavelength, you really have to do some engineering to change the wavelength of the OPO. Here we can just simply change the vapor cell and then work with cesium, for instance. Or the idea of the project is go a bit further, and why not using a vapor cell with a mixture of atomic species? That would allow us to produce or to pump with 2 different wavelengths and then produce 2 different twin beams. And in that sense, one system is actually producing squeeze light simultaneously for 2 different species for atomic magnetometers. So this is very briefly what the project is, and this is going to be developed at the Federal University of ABC. I just started in January. So the project involves, or the idea is to have two PhD students, 1 postdoc, and also 2 undergrad students. And we have fellowships and scholarships for these students. And so anybody that is probably interested in this kind of project, you are very welcome, and you can get in contact with me. And well, that's more or less the idea of the I hope I didn't spend too much time, but okay, thank you very much.
Thank you, Hans. So now, I invite all the speakers, all the guests from the session to make a kind of roundtable here, so we can be a better position for the audience to ask questions and for discussion. We have to improvise a little bit here, but it never is. It has this name, but it never is. Sim, yes, please. Carmen, Inácio, everybody here. Ah, nós. So, as I said in the beginning, this is an informal meeting. It's more of an opportunity to present to students, new young researchers, community in general, the kind of things that, I mean, the choices here you've seen today are all things that are currently going on in labs in Brazil, not just in São Paulo. And I think one of the ideas, not just present the potential of quantum sensing as a broad area in general, but also to create a community, a sense of community, to know what each one is doing and see the opportunities for collaboration. I think, I hope you appreciate how much connection there are between the talks from today, different platforms. Sometimes people don't even know what's going on in the next city or even their own institutes. So I think this is the spirit for this conversation. So I'd like to invite you to ask questions in general. If people are online, also please let us know if you have a question. If you want to speak or type in the chat, somebody will, Dario is helping us to see. Então, please feel free to ask any questions you think or curiosity you have for our members here. So who wants to start? Marcos, please.
Hello. I am a student of Professor Daniel, right here. And the question I want to make is, is the level of readiness that all the technology that you have just talked about, like this morning and just right now, are? Now, what's the level?
I've shown.
Let me just make a compliment. So you talk about like this readiness, right? It's a very private company term, right? When you talk about technology, right? And things here, they lend more to a more skill-based research, right? side of things. And so there is still a lot to do, right? But I don't know how much this can be made into product or something that private companies can really start doing, using for technology, for applications and so on. So it's a general question for everyone.
Okay, I'll probably start saying a very dispersive answer. That's to say that there is different levels, depending on, you can see gravimeters already being replicated, so the readiness level is 9. So it's already in the market. So we have private companies. Philippe Bouillet already left even the company because they are dealing with commercially. So they. So and then you have different the proof of concept or parts. I would say depending on the application you have it, but you have to wait. Also, the use. I think the most important part is it's about the use. Sometimes we are trying to find the more precise measurement, but someone next to you, they don't need all these. Okay. Yeah. Thank you. Thank you. So people sometimes they don't need all the precision that you can give to them. They just need some order of magnitude below. It's already. It's like and the use is limited by the environment itself. Like for atomic clocks, we are talking about 10 to minus 19, but troposphere prevents us for using for less than nanoseconds, so it's 10 to minus 9. So let's say this for a short term. So this.
I thought I could speak loud enough, but it's okay. That's to say that not always quantum science is necessary, right? It's more or less like this.
It can be, but I think there are readiness levels that are already very advanced. And
I think Professor Carmen wants to complement.
No, yeah, I think my answer would be on a similar note, right? It depends on what your sensitivity requirement is, but it also depends on what the particular application is, right? Because it's one thing to be ready on a commercial scale for academic applications or for research lab applications, and it's another thing to be a product that you can buy off the shelf and use it as an end user, right? So I would say for NV, for instance, it's at that level of readiness where it's commercially available for academic or research institutions or research and development labs and whatnot. At that level, it is. It could be a better system, but you can buy it. But it's not an end user ready product, right? So it's a different, it's a different thing. I don't know if.
On behalf of my experiments, you have seen the optical table, and this is what I call a quantum sensor. This is not ready to be implemented in a smartphone. So we are more interested in fundamental research, proof of principles. On the other hand, I know that other groups which are also working with similar system in Birmingham, for example, or in Amsterdam, they are trying to miniaturize quantum, matter wave interferometers. They want actually to make a device that could be sent into space. And they are putting a lot of energy and efforts into miniaturizing the lasers and the vacuum cells, but it's a lot of work. I mean it takes decades to go from a proof of principle to some commercial prototypes. It's not an easy task. And here in Brazil, in this area of physics, matter wave interferometry with atoms, we don't have yet facilities to do that. No.
Well, from the point of view of what I showed in superconducting qubits and so on, this has been in the let's say developing for the last 30 years. So IBM and so on, they have their own qubit superconducting computers, but the access is very limited. You have to pay a lot or so on. And as Marcasa showed, there was a directive from the Commercial Department of US last year prohibiting, hindering a lot to acquire pieces to develop one. So, for instance, in our case, we need some very special amplifiers to put the signal inside. We have quoted it from an American company, and they already contact us saying that they cannot sell anymore. So we are searching European companies to provide. But this is one thing that we have to put labs and people working on this to reach perhaps the same academic use or whatever. And also, in the point of view of algorithms, so what you can do with a quantum computing, it's still in the proof of concept saying, we can make a factorization of the number 38 or whatever. So what you will do with that, there are claims that they are developing some programmable quantum computers that will be in the market in the next year or 2 years. This is a promise. If they can do it, it's really, it will change some paradigms. So, but we are following the developments. We need to follow. We need to have people interested in working on this, and I think that's the main job we have to do.
Well, from my side, I think one of the advantage of working with vapor cells, different from the case of cold atoms, for instance, is that the system is relatively more, it's easier to get into small sizes, right? And so part of the project is to develop these magnetometers in very small sizes. As you can see, there are other companies in the US in which you can already do that kind of things, right? So depending on the application, is relatively easy to try to go in that direction and look for that kind of miniaturization, for instance, right? But of course, that's one of the advantages with vapor cells. But when it comes with cold atoms, then it's get complicated again. But as we were discussing with Gustavo, and as you were mentioning, it seems like since we don't fabricate these vapor cells and we need to import them from the US, they have now this instruction of they cannot sell it. So apparently, then we need to start doing this kind of technology, right? In the case of vapor cells, differently from the case of chambers for cold atoms, is not something that is very difficult in the sense of doing the fabrication of the cell. It's not itself is very difficult. So it's something that it needs to be think of. We need to, from my side and from our side, we need to think about how to go in that direction and overcome these kind of things, right?
Okay, so I think from our side, in terms of like the optomechanical device, as a quantum interconnect, the readiness, so to speak, is not there yet. But there are companies, actually, like one of the collaborators, Simon, has a company. I was just looking on the cell phone. They had already like 30 people working on doing an interconnect between superconducting qubits, because one of the things that, one of the challenges that, for example, IBM faces is that actually it cannot communicate one dilution fridge to another. There is only a single experiment that did that, but they actually built another chamber to have a coax cable, also in millikelvin temperature, getting like data from one to the other. So if that's, there's always a if. If that's the system that should go as the champion for quantum computer, you need to communicate like different devices. And the way to do that is optics. That's the way that I see it. And there are other solutions to do this interconnect, but still up to date, the one that has the higher coupling efficiency is optomechanics. So, but the readiness is at the level of startups, I would say. But on the optics side, I think all the integrated optics then is like already ready. There's like lots of companies, and you can design a chip, send it out, fabricate it outside, purchase. But I have to say the same thing that they are doing, like we need to do this here in Brazil. So when you start to see what's going on worldwide, we need to have this technology on our hands, because it will not come for free, and actually will not come even if you pay it. I think that's the message that we are getting here. So I think other than like research, etc., we need to also stimulate engineers, as Marcos was saying, because they are the ones that actually know how to fabricate it. That's the true thing. We just know, like the physicists, like myself, I'll put on the line here. We know how to do like a device, like the golden one. But how to scale up that, you really need to have like very good engineers. And I think we do have it. But they are always going through like administrative stuffs on companies. We need to bring them back to make like real devices. Okay? I was too hard there.
It's just a question of sovereignty, right? Like.
Okay, on my end, this field of quantum inspired is very recent, and it's very started. There has only been a few proof of principle. First of all, in super resolution microscopy, we'll never get to like consumers or users like this. It's more like academia to academia thing, or like research lab to research lab. Actually, my PhD supervisor started a startup on these ideas, but he's a bit of a risk-loving person, and I think it's a bit too early to make a startup on that, but he made it anyway. But it's actually a technology that it's compared to all the other ones which are inherently quantum. This is just actually a very simple technology if we manage to make it work, and if we crack the code to have a proper implementation of it. I don't think it would take long to reach a mature state where it can be used by other labs and be used for its intended purpose, which is other research or being sold to Zeiss or something like some big optics company like this.
Well, about Rydberg atoms, I think I know the two companies in the market, and they have a product. You know, they are, especially the military are interested, you know. I could see that we could be interesting because we have an airplane company, you know. I wish I could put a radar system in one of their airplanes, you know. But that's the problem. This requires a lot of technology that we don't have at hand. For example, we don't have a laser. You know, so if someone like Toptica tells us that they are not going to sell us lasers for that, it's over, you know, or cavities, you know, all this kind of stuff. We need to develop those things, you know. What? Yeah, it's an infrastructure for everything. Otherwise, we're not going to make it. Yeah, in general, like even for this simple Rydberg atom, you need two sensor. You need two lasers, you know. So we would need to be able to make the lasers. Otherwise, if you depend in a private company somewhere else, they could tell, no, I'm not selling you the laser anymore, you know. And then it's over. I don't know if you know also, but last week it came out in Nature that Michel Lukin got $230 million for his quantum computer based on Rydberg atoms. I don't know if that's going to be really a computer, because I know, I think you know one of those guys that work for them. It's this guy from, this Italian from Tomasio. Tomasio is there, right? I think he's getting a lot of money, but anyway. So I don't know, they're gonna, I think someone told me that their computer costs $20 million right now, and you have to pay extra $5 million to keep a person running the computer for you because you cannot open it. It's a black box and you're not gonna allow to open the box. You know, so only this guy. So we need the infrastructure.
So following up a little about what you said, and especially Thiago said, on this bridge between academy, so we need infrastructure, but I don't feel that we want to do this. So the question, or maybe yes, so my question would be, do you see yourselves in a near or far away future starting a company or on some subject, or do you see yourselves like putting, I don't know, helping someone doing this? Who would be, do you see yourselves taking part on this ecosystem somehow outside of academia?
I don't know. Someone told me, Ben-Hur told me that we can go up to level 6 on readiness at the university. Then after that, it has to be kicked out. I don't know. But most I can tell you is that I'm trying to motivate people. I don't think I'm going to do a company. But I will be happy to be rich, you know. I will not complain.
Well, at the end of last year at CBPF, we had the development of a permeameter, a water hydraulic permeameter. It doesn't have to do anything with that, but with scientific instrumentation, which was developed in the labs of CBPF with Embrapa and sold to a company in a transfer of technology contract. And it was guided by the laws of innovation that are vigorating in the country. So everything was legal, was well done. And they are starting to sell the first units now. And there will be a kind of transfer of resources, money, and so on to the institution, to the developers, so on. And this was developed by one of the technologists in the Ministry of Science and Technology. We have researchers and technologists. There are two careers. And he's pretty much involved in scientific instrumentations. And this worked. I mean, he didn't left the academia, but he was a very active participant in the development of this technology. And for sure, this is what we would like to do, at least in the units of the Ministry of Science, Technology, and Innovation. So the innovation is in our mission. And I think most of the universities has a place in which startups can start and go. And so I would say that it will be nice and it will be very healthy for the economy of the country if we can motivate the young people like you to pursue that objective as well. I mean, it's not only academia and only research and only innovation, but something that talks between them. I would say that this is a nice thing to do.
So we just heard Toptica. Toptica was born inside a lab in Switzerland, and now is a company that sells like millions of dollars. So I think there is opportunity. In terms of Brazil, like you have to remember that the law of innovation is quite young. Actually passed on the Congress like in 2019. The regulation. The law existed before, but the regulation was just like 2019. And I think this will start pushing towards more and more of this kind of subject. And actually, we don't need to make a product for other people. We can actually, there's a large market in Brazil that actually, it's hungry for that, for other things. Of course, that if you ask me, like, are you planning to go? So there's always like this curve, like as you are getting old, you don't want to get risk until your children has like 18, and then maybe you can go and get larger risk. I'm getting no risk now because I have a very young kid, so I don't want to get too much risk. But I have to say, like, I think, and that's something that maybe at Unicamp, there is a push on this direction. Because the idea of innovation, it has to be, so to speak, teach it. Because it has to be embedded on the how can I say, like on our culture. Is not yet truly embedded. Because if you get the guys from softwares, as we're just like crack the software there, but the guys from software, they do go out after like companies, and they do like go after and do their own company. Maybe because it's a smaller endeavor in the beginning, because you do by yourself, but iFood is one of the largest companies in Brazil. It was a startup company, you know, and it was based on one old student from Unicamp that actually went out and started a company. So I think there are room for that, and we are getting better on that. And I would say just go for it, because we do have the mechanisms to support it. Not only FINEP has also, and also the Minister of Science and Technology, but even FAPESP has here in the state of São Paulo. There's the seed money to start a company, to start producing small things. And actually, of course, after that, you should go afterwards. Daniel.
This is the marker that I have to place. I don't believe that all the professors, they have to go to the private sector or start startup companies, or they can take part maybe. And what I think is that the so-called Death Valley that appears in all the innovation summits and so on, this has to be supplied with people that are produced, let's say, from the universities, from the labs, from like physicists. Because what we have in Brazil sometimes is the culture that if you are in a physics course, you go to the academia, and it's not the case. You don't need to have like we call here. I am an engineer, and we have the registration. That's call it CREA, the Council of Engineers. So, but you don't need. A lot of companies, they have only one engineer registered, and everyone there, it's an analyst. So you can have technical people and very good technical people working in the companies, the private sector, but we have to have an environment to do this, because to get the risk, and to get the risk in high tech, we are always used to these buzzwords, and so there is the joke about playing bingo. So if you have 3 buzzwords in the same phrase, you win. So you have all these deep tech companies that are starting, because we are so used to a lot of companies that are, and it's not a fault from them, and I'm not really saying any bad things about these companies, but when you develop an application for a cell phone, for example, the starting budget that you need to have, it's very low. If you need to have a read bare atom sensor in the very beginning, so your investment in the beginning is a bit higher. Maybe the solution could be a hybrid solution, like universities providing an embasement to start, pre-incubation and so on. We were discussing this a lot inside the USP also. And the solution, we have to find our way to provide the good base to start these startups with a lower risk, because they need somehow more equipments and more technology, meaning more money.
Yeah, if I can interrupt just a little, this was what I was thinking a little. So there is a kind of, I think there are some challenges related to hardware, specifically hardware startups. and related to maybe production. So for example, I know in Unicamp they have lots of facilities. So I don't know if we could think about ways of bridging this gap or making smoother passages for people that try to do like hardware. Because yes, iFood you can develop on your computer at home. You stopped college and then you go to your mother's house. You stay 1-2 years and then you have iFood. But I don't think it was. I don't know if it was like this. Probably not. But yeah. So it's different from so Toptica or yeah. So I don't know if there are strategies that we could have been doing better because we have some gaps, let's say, in Brazil. But I think we have really good people, good ideas, and good things going on in academia. So comparable to best things in the world, as we saw here. On the other hand, from the hardware companies, at least we are maybe not there.
Yeah, I just keep the microphone. But maybe it's something about looking for the environment that we have in Brazil and who are the real investors that we have. Because we have agriculture, what is the subject that they are nowadays interested if they have the money to invest, for example? I'm not saying that they have, because they are not always in the green light. So we have to understand how much investment that they can do, for example, and another kind of, let's say, clients in the field. Because we are always taking a look worldwide, but the worldwide investor is not necessarily the one that is going to invest in the Brazilian company that will be the startup. So that's the point. We're making the exercise in home and abroad. Of course, if you have a very successful startup, you sell abroad, so you export. I will stop. If not, I would talk a lot.
So let's comment. That's why I think the universities are important, because we do have the infrastructure. Like all the lasers that they are saying, all the readback atom, they are there. No, like I think that's what's missing. Like we are missing just this little jump. Like okay, bring the startup companies to use. I was like Toptica, as I mentioned, and also this one from our collaborator, actually was hosted inside their lab for 2.5 years. Only now they are off. Like the microfabrication facilities, there is no company that I know that was made inside a university that make their own microfabrication facility. All of them use the microfabrication facility of the university. All of them, for very cheap money. And then once they have like the strong to go abroad and actually to go out and then start doing it yourself, then they start paying as a big company. But so I think that's again, like I'm very positive, saying like, okay, I think we're starting to get track on that, and but we need to motivate the next generation to say like, okay, here's the infrastructure, you can do it. You know, I can put an optical table for you here, and you do your stuff here. You use the microfabrication facility and go forward. You know? I think that's what the university has as a mission, to help this first. I would say like no, it's not like Death Valley. It's just like I don't know, like a death like ocean, because for hardware is very expensive. But if the universities can jump in and help in this beginning, I think then we can bridge the gap.
Well, giving continuity a little bit on this talk and going against what you just said, Thiago. Me as a PhD student, I feel a really big lack of infrastructure in a few areas, especially in experimental areas during the research. On my case, is specifically on the micro and nano fabrication. Being at Unicamp, we have access to probably the best places in Brazil, and still we have many difficulties to or use them or really low access to a few sets And sometimes even we have only one machine that does that process, and if that machine breaks, we can stay for like a whole year without access to what we need, and that can make disrupt a project of a student. And before thinking go to some startups, usually you have the development inside the university, and for that you have to need to have a broad access to the development facilities, right? And in a medium time range, I think we could talk about initiatives and projects that is being already going on, but I think that is able in like in a scale of 5 to 10 or more years to have a really different scenario than today. I wish to ask you guys what you can see, what you see, what are maybe realistic strategies that we can put on for students that are already doing their projects or about to come in a few years that could change a little this scenario, like maybe invest in a center that won't happen so fast. But maybe you invest in scholarships that could send these students to use centers that already exist and we could have access, and brought that, bring that knowledge that the student will gain back to Brazil later. That could be an interesting strategy. So I'll talk about that.
Okay, I'll try to be fast and then go along with all the others. So first, I think, so as a researcher, a perspective as a researcher, what I have been done the last 14 years is a mixture between fabricating in-house and using other people's facilities. So, and I think that was, up to now, was a good strategy. So we fabricate some of the things, everything was done inside Unicamp. Partial things outside of Unicamp, design and then send it out and test, and collaborators. So I think that's, as a researcher, I think that's what we have to do it. In terms of like a research infrastructure or a multi-user infrastructure, the fact that we are here now shows that we are start getting aware of it. The fact that we do have now like programs that look into quantum, and then everybody's saying, okay, if you want to do quantum, you have to have like infrastructure. You have to have, it's not infrastructure, it's more like an ecosystem. So the fact that we are starting to question these things, I think is also already a progress. And of course, it will not happen in 1 year. Like a building doesn't grow from the floor in a single year. But we do have the equipment. I think that's something that sometimes students do not realize. Only realize when you go abroad. We have a tremendous equipment list in our universities. We might not have a beautiful building, but in terms of equipment, we do have a very rich environment. For the microfabrication specifically, I agree with you. We need to have a single or at least one first, like a multi-user facility that has everything and then can run over and over. We have been trying to do this the last few years. It's not that easy because there's always this naive idea that a multi-user microfabrication facility will pay itself. That's never gonna happen. Like I visited the one in Delft, they have Microsoft inside it. That's how they pay it. Microsoft has half of the clean room that you cannot enter. There's a blank. And they pay for the bill. So it will never going to happen. So we need to convince the public players to say okay, we need to make that as a multi-user facility so everybody can use it, but it has to be, most of the money will come from the public. There's no way around. And that happens everywhere. Go to MIT, same thing. Go to Caltech, same thing. Harvard, same thing. None of them pay their bill by themselves. There's always some very large chunk of money that comes from the public. investment. So we need to make people aware of it. And to show like, look, we can do very nice thing if we have like this kind of environment. Okay.
Let me probably just about the what are the opportunities for students to go out and learn these kind of things and come back and develop this kind of technology. Well, FAPESP is already doing, for instance, my project is part of the QTA program of quantum technologies led by FAPESP, offered by FAPESP in the program. So one of the projects is my project. Also, Simon here is one of the awarded fellows that won this kind of projects. So for this kind of program, there were 5 projects awarded for quantum technologies. So this is an initiative for actually try to attract people and try to, and the idea is to participate in this kind of events and really gather and try to communicate for the students that there is a possibility and that the efforts are going in that direction, I think, nowadays. FAPESP is one of the leaders on now with this, but I don't know if CNPq or he's also offering kind of fellowships to go in that direction. So I think probably, I don't know specifically for what you're saying, but in that sense, there are programs that are now being offered by agencies that goes in that direction. The idea is to do projects now, for instance, if I'm right, but Gustavo can correct me, this year or next year, there's going to be a second call for the QTIA, for joint investigators for QTIA. So there are these programs, and it's going in that direction, I believe. So.
Yes, very briefly. So these kind of problems depend a lot of the area of physics. So, for example, in cold atoms, we don't make use of any multi-user facility. We don't have multi-user devices. So everything that is in our lab, we buy for this experiment, and we don't share with other people. So and if we don't. And if this device, the device that we need is available on the market and we have the money, we buy it. If not, then we have to build it. Okay, so for example, we have lasers that we build because it's cheaper to build your own lasers, no? Or circuits, no? that are not even available on the market, that you have to invent and to test and to make working. So this kind of problems depend very much on the area of physics. On the other hand, I mean, by developing your own stuff, your own circuit, your own lasers, this is how you get ideas on where startup companies or spin-off companies can start. You mentioned Toptica, which a colleague of mine, former colleague of mine, Ken does. It's a German company, actually, not a Swiss company. He started exactly looking into the lab, and he was going around and asking what are these little boxes here? You have many of these little boxes on the table. What are these? No? Apparently, you need lots of them. So, is it worth maybe creating a company which makes these little boxes? And these were ECDLs, no? So extended cavity laser diodes, which is how Toptica started. No? And there are many other examples where this worked. Okay, I think the technology is developed in our labs. It's basically doing the step that's taking the risk and taking, trying to get some capitals and then going around and try to convince people. I have a laser. It's a lot of work. In former times, it was typically a diploma, master's thesis. No? So you make this lasers at this wavelength. This is your thesis, no? And this is a lot of work and which is not very interesting because these lasers have been already developed in other labs, and so it's redundant if you reinvent always the same type of lasers. No, it's easier to buy it if it's there. No? So I think it's a good idea to identify what are the needs in the labs and try to find where there is a market opportunity there. No? And this works with many other examples. Tor Labs, the same thing. No? Alex Cable started with this mirror mounts, no? So optical mechanical devices. No? And there are many, many other companies in Europe, in Germany.
Yeah, maybe one comment, and this may be very naive as a newcomer, so please don't laugh at me in 10 years if I regret what I'm saying. But I think there's more infrastructure that we know of typically. So as a student, I don't know if everyone's familiar with it, but I wasn't. But there's a huge database from, I believe it's from the Ministry of Science and Technology, but there's a database online where individual labs can host their equipment as multi-user equipment. So if you're in need of something, go look it up. If you have things that you would be happy to lend to other people, add it to that database because it can be very helpful. But there's more than we think, and I think also related to the last question is a change of mindset of how we operate, right? That of course we don't want to be purely providers of services. That's not what we're there for, but it's a change of mindset of how we operate and what we're willing to share and collaborate on, both with other researchers and students of peers, but also with startups and so on, right? It really requires a change of mindset.
Thank you. No, concerning this platform that Carmen mentioned, it's there. It's organized by the Ministry of Science and Technology. And if you want to get money to, let's say, maintain a certain equipment in one of the calls of FINEP, which is one of the agencies that give you money for this purpose, you must have your lab there. Otherwise, you cannot ask for the money. So there is a huge number of labs listed there. Some of them are including the no operating labs are listed there, so you have to be careful because you can access it and no operating. So, but they are there. You can search and they are there.
It's called FINEP. Yes. Just one point, maybe it's not Marcus who will kill me. He's already. Just a middle term, maybe is that we have to think about the right business model that we can have. Let's say, sometimes we think about fabricating things to sell the device. And it's not as a software, they sell service. So, because this decreases the quantity that you need to have of device. So instead of providing atomic clocks, I can provide the synchronization source. So instead of providing the Rydberg sensor, you provide the service if the guy needs every day, every hour, so they can acquire from. I mean, this is an exercise that you have to do. I say so because at home, to finish the joke, I am the engineer and I am the academic. My wife is the physicist. She is from the private company, so she has her company. But they changed it. They started thinking about fabricating spectrometers to sell for Leib's spectroscopy. And nowadays, they are doing a characterization as a service to sell carbon credits. So this is completely different from the start. So they started doing the service. If afterwards they feel that they can change, because the starting hardware is very expensive. So that's why, and you have the reason, you are completely sure. But we can do, with this, we maybe can optimize and do the best with what you have at the moment.
Yeah, I have a quick question, and I'll try to poke you guys on one aspect, which is, as a scientific community, especially in the physics realm, what I see a lot is a resistance towards applied research. You often see yourself, and that ourselves, referring each other's projects, right, within the context of funding agencies. And more often than not, and maybe I'm adding my perspective here because I've been serving FAPESP on this review board for some time now, and it's very common to see more applied-oriented projects come in and receive relatively bad reviews, saying, okay, this is not, there's no Nature paper coming out of this, there's no PRLs coming out of this, so this is too techy. So there is a sense in the physics community, at least, maybe the engineers are a bit more relaxed on that, and something I've been criticizing, which is, of course, we all enjoy publishing high-impact journals, working on trendy topics, getting invitation to give lectures on international conferences. But with that, we are certainly serving an international physics agenda that not necessarily addresses the problems we need to actually solve for the actual market. You mentioned agriculture, right? Brazil has a specific agriculture demand and is not publishing work that addresses the global agenda that will be solving the problems that Brazilian agriculture needs to solve. So what I want to bring in is, I would like to see yourselves, do you see yourself as a person that would favor a project that has a very techy, sometimes industry-oriented project, or you would yourself see, okay, this is not top-notch science, and I tell most of our community does that, and I know because I see the reviews from the projects. So it's kind of a roadblock, right? Because if we want to see a change in that, the first thing is to change the mind of the community and start to praise those projects. Okay, this is maybe it's not a Nature paper, but this is solving a problem that has a potential to become maybe a heat bag sensor, maybe a optomechanical accelerometer, but will not certainly publish a top-tier journal because it's not novelty anymore, right? And it's by definition, if it's mature enough to be put out into market, it's certainly no Nature paper, right? By definition. So it's sort of a contradiction we leave. That's what I would like you to comment.
Can I answer that after I get my review from FAPESP? Because I have submitted a proposal on this Rydberg atoms, and I replied, the referee did not like it much, and then I replied, and I will see what's coming out from that. But going back to your question, I can tell you one part that it's a problem, because although I'm not involved with neither of those two companies, I know what they have been facing. You know, like my former student complains that he doesn't publish papers, or, you know, he doesn't publish as much as he would like in a university job. My friend that's from the other thinks that when he hires people, you know, sometimes people are thinking, still with the academia mind, that they have to come and they have to publish papers. And if you're in a company, that's not important. You know, maybe it's more important to have patents. You know, so I think that we need to change that mindset also. Even for the people that are in the universities here, you know, if they are doing good applied science, you cannot ask them if they are doing a very good, maybe especially if it's going towards to a product or a service, you don't expect them to publish papers, right? I know it's hard to judge the quality, but we have to change that.
Once, if not, I will monopolize. That's again. Sometimes I try to exercise empathy from both sides, from the referee and from the guy that is asking for the money for applied. Maybe it's not just someone saying, "Oh no, this is not pure science" and so on. But we have a limited amount of money for basic science. If we just, let's go to the extremes, like I go to apply the science, and then I go and I just kill the source. This is not something that, this is something that we have to balance every time. if we take money from basic science, but it's not necessary to go to nature. Sometimes you take a lot of time to publish a good paper, and we're not just about numbers only, right? On the other side, maybe we have to exercise taking investments from the private sector to be directed to this kind of science. So the agencies, they have to exercise themselves to take good, FAPESP do this with Shell, with big companies, IBM, for example. And this is a very good essay, let's say. And so this is a middle term every time. It's not just taking, so this is not to be shallow, taking some arguments, some sparse arguments from each side, but trying to understand why people are refusing applied physics projects sometimes. Maybe they are afraid. This is an instinct that we are going to sink all the money from basic science, for example. That's I don't know. That's
Comment a little bit. I think I can comment a little bit on the same line and maybe play devil's advocate for a second. But I think there's two things, right? There's one thing is creating new technology, and there's another thing which is just as valuable, but applying technology towards specific problems. And I think both are in Brazil's interest, right? So you shouldn't give up one at the expense of the other. But if you look at least in the solid state literature, right, the vast majority of the highest impact papers that are out there involve a large part of instrumentation, right? If you want to measure something new, if you could measure with what's available, it's been done, right? So if you want to measure something new, you need to develop a new type of instrumentation, which ultimately leads to new technology and so on and so forth. So I agree that there's a balancing act, right? And if you think about the agro-business problems that are out there, agro definitely has money that it could spare to invest in physics research, but we don't have the mindset for it as well, right? So if I can play a little bit of devil's advocate here, I would say my argument would be that, right? That we need to change the mindset in what type of funding we are using and we are harnessing, and maybe reach out to these companies more with problems that are useful for them. But there's definitely a role for public funding, which for projects that are ultimately higher risk, right? And
maybe I can comment a little bit also. In the past, in Germany, it was not well seen that public funding, like the DFG or so, would put money into applied sciences, because if something is developed with this public money, and then it's the people who are going to benefit from it are Siemens and Daimler-Benz, they should do the research themselves. They have big money. Why should the public money be wasted in finance and subventioning private companies? No, I think in Brazil it's maybe a little bit different. Also, it's different with respect to spin-off companies which do not have this amount of money available. No? But normally the public money should be, at least it was like this in Germany, should be invested in projects that have no other funding. No?
Difficult to answer. I would say that I'm bad at judging innovative projects. So in terms of breaking the bubble, I kind of agree that we have to be a little bit careful to not go all the way on the other way, to just say like, okay, only applied science is worth money. And finding the balance is not quite easy. We have seen like lots of presentations, even from FAPESP, that showing like, okay, the amount of private investment is small in Brazil. So the amount of public investment percentage-wise of the PIB or the GDP is smaller than the OCDE, but it is still on top, almost on par of like the largest one. But the private sector, it does not apply the same amount of money. But I have to say that we should start trying to poke this bubble, even with the public money. We should just separate, say, okay, there's a specific program, it is for that. Let's go forward. Let's see what we can do it. So I think in the state of São Paulo, there's a CPE, which is the Center for Engineering, that they are trying to do that with the companies. And I think that's one way to see it. But we just to I think you cannot have the same community judging both of the things. I think that's my takeout. It's very difficult to have the same person judging the two kind of projects if they are that far apart. So maybe just like, okay, let's make this a technical problem. And who wants to apply for that? And that's it. So I think that's my...
Let me just, one comment on that is last year at USP, there was a colloquium discussing this topic in particular because the discussion was that at least at USP, several groups and many of the works of research at USP, it was addressed for academic purposes, right? Like really fundamental science and all this stuff. So just now they are discussing how to move towards something fundamental and going into the direction of more applied, because for at least 30 years, what it's been shown here is that at least at USP here in São Paulo, the community learn how to approach problems, how to work with the background of the students to really attack problems and doing research. Now it's time to move into the direction of how we can use, now that we have the community, the academic community has grown, how we can actually go into the direction of use that into the applied science. Because for several years, it's like growing this academic community in fundamental science, but now I think Brazil needs to move, to move into the direction of applied science. So, and as Thiago said, I think that's the way of trying to look for the balance, because for a very long time it was like really just the academic science, right? The fundamental science. And so I think that was the discussion at that time, and I agree with that. It's time to really try to find the balance.
There's no discussion on copies about that.
Yeah, exactly.
So I think we'll pass to the last question, right? I just want to do a quick comment before. It's related to the question that you did, and more or less to the answer Philippe gave also. I think in a sense, so the students have like a privileged place in the lab also, in a way. I mean, okay, not privileged because you don't have permanent position. It's not very. But on the other hand, you have your career in front of you, and not every time maybe you feel like I really want to do research in the end, but maybe you feel like you have a good idea, but you don't know how to start. So I would say that FAPESP has grown in the last few years to a higher flexibility, like you have this treinamento técnico, scholarships that are not directly related to doing master or doing PhD. So I mean, I would say that if a student has an idea and imagines that some laboratory could host this idea, I would say that the student should find this laboratory and should make an approach, not an approach going to the lab to ask, do you have a project for me? But if you go to the lab after some years of research and say, I have an idea, I would want to develop, I would want some years doing this in the infrastructure, I would say that this could be I know lots of, I think most of people that are here would say, just come. And I think this could be, a possibility, because sometimes you don't know how this, how the infrastructure works and how you could access this. But there are ways to access this infrastructure for some years to develop something. So I would say that an idea is valuable. So yeah, you could come.
Okay, so the last question, the very last question, I think that's appropriate, so please.
Well, before I introduce myself, can you tell me how many people here in this auditorium are non-physicists, engineer? Or no, I mean, yes, no, yes, who? Like social scientists, psychologists, you know? Okay, so I'm the only one here. Well, I actually have degrees in engineering, 3 titles in production engineering, but I'm also an economist. So, well, let me introduce myself. My name is Luciana Pereira. I'm an associate professor at Federal University of ABC in public policy, especially in science, technology, innovation. I came here, I have not been invited, but suddenly I realized, wow, I thought I was in quantum technology. In the discussion would be about, and it was, of course, the basic sciences of quantum technologies. But it was very interesting to see the round table here in the discussion, because I actually have studied that. I have studied, my PhD was 20 years ago when I started. I was studying CEPID, FAPESP CEPID, and specifically I studied the companies in São Carlos and Campinas. So if you ask me what I think, when I look back, I don't like to look back at my work. So it's good that I see myself as a social scientist, because in social science, that's okay. Maybe when you don't have to be exact, 2 + 2 is not 4. Because I thought that I had a lot of hope about these companies and how this would transform. I have not followed. I know Danielle is there. Maybe I should go back and take a look all these years later. But when I see these PEP, all these talkings here, now that I'm turning next week 15 years at UFABC, I see in a different way. First of all, the question about who are these people here, because it's important to have people like me. And the guy is like the student who said, no, I disagree that as a physicist, it's not wrong that you are going to the lab and think about the problem. That's a lot what you guys are doing. But it is important that these calls, they have people that they don't understand anything about that, but somehow they can talk with each other, like people in public policy, in business, but in psychology, different mindset to think about how we are going to build this ecosystem. Because I'm sorry, it's sad to me, maybe because I'm getting older, just turned 50 last week, but I don't, unfortunately, I'm getting old and I don't see this country that's full of, we are so rich. I went to MIT, my sandwich, so I have seen it was part of my research. Because I want to see, okay, what they are doing there that we have to do here. And then I realized we are always looking. I was that person talking about all this concept they made there in this university that are very nice. But we also have to look at our reality, our country. We don't have the same history, and we know all the problems we have. We have one of the countries with the largest social inequalities. That's part. I know I don't want you to think about that. Keep thinking about the physics, the quantum, and everything. But I have to tell you that's also important to reach what you guys are talking. We need companies because I need to buy in the lab Toptica, Tor Labs. They are there. They are not here. So that was part. The geopolitics is part because they say, no, I'm not going to sell to you. So I don't want you to answer that. But we need to work together with people in a different, with different mindset. And also stop. Now I also think about the World Cup in 1958. That was the very first World Cup that we got in Sweden. Because we were ashamed of the players in the past, because we didn't play like Europeans. And then in that World Cup, somehow we are playing like we are. We found a way, and then we became champion. Everybody thought that was beautiful and elegant, and we succeed. So I believe that we have to stop trying to not copy. That's also a part of knowledge, but that we need to find our own way. We need to get together with people, different mindsets, and find a way for this country to make these technologies and many other technologies to happen. And last point. On Saturday, I was in my course. We have already started our quarters last week, and then I have my lecture on Saturdays because our students, they work. And then we have this course on Saturday because they can come everybody together. And then I was mentioned, I mentioned that Itaú, a long time ago, they realized that it was important to have computers and information technology in the very beginning of the PC and this technology, because they knew that the bank, it wasn't about the money, it was about the information technology. And now Itaú, they are, if you look around, they are the Brazilian company investing in quantum computing. Because like 40, 50 years ago, they already knew computers would be their business. And now they know that if they want to manage this quantum compute, that they will be out of the business, their business. So they are, in Brazil, the company that are investing in quantum computing. So I said that in my lecture. And then one of the students in public policy, humanities, Bachelor in Science and Humanities, turned to me and say, well, but that's even, okay, Itaú is doing that, it's great, but we are already late. So undergrad student, and I was like, well, I hope you are wrong. But I'm afraid that I have studied all these cycles of technology, and I'm afraid where Brazil is always, like in the government now talk, you have to do our own artificial intelligence. That was my comment. When the other countries are, okay, we have our ChatGPT, whatever, DeepSeek, right? I don't know. Then we say, okay, that's great, we have to start. So that's why I'm saying that we have to, everybody, I mean, when I say everybody, there's different mindsets, the government, the private companies get together to try to change this pattern that we have been following for different generations and cycles of technology. Thank you, Sergio.
Thank you. Thank you. So we're, of course, late, but I just want to comment on there is a message on the chat.
Several, actually.
Okay. Can you take care of that, Dario?
So this is the first one.
Okay, I'll read it. Or is it this is being projected as well?
I guess it's projected.
So everyone that will see the video later will see that, right?
I guess so.
Okay, so I guess so we can just move them. Thank you, Nara. By the way, Arthur.
Okay, this might prompt an extra discussion.
This is a good idea to foster public companies. Say. So somebody wants to address this question, maybe Thiago? I'm sorry to cut it a bit short. We are a bit late for the poster session, so.
So we did had that in the past also. Remember, like Telebras also was a very large company. And then on the 90s, when we opened the market, Telebras could not keep up, so it broke. But we tried to build one also, SAITEC in Brazil, in the south of Brazil. It went well for a while, but then also had some problems. But again, like after the pandemic, people start thinking, again, maybe we need to bring the knowledge back. Because I don't know if you remember, but during the pandemics, even cars couldn't be sold because we didn't have microchips for the cars. Has nothing to do about the motors, nothing to do about the iron or rubber. It was microchip they couldn't put inside the car to make it work. So I'm not saying that we need to make a public company in the way that it was, but maybe you were saying about Petrobras and Embrapa, they are mixed. So maybe in that situation, I think might be a good idea.
Okay, and then there is an extra, I would say, comment.
Okay, so this is another comment. All right, okay. So let's wrap up by thanking to thank all the speakers and the panelists again and all the questions. I think it was great. So thank you, everyone.
Just need to advertise something. Is on the 17th of March, ICTP-SAIFR will be hosting a joint session with the APS, American Physical Society March meeting. And similarly to what happened last year here, there will be a joint session, which means there will be a lot of people here in ICTP, including yourself, because I'm counting on you to come here. And you can look up at the program. Do we have the computer that, can you put the program for us, please, Dario?
Let's see.
If you go on the web, if you go on the web.